maybe that's a signal that the transition from lecture to lab is one that should happen sooner than later. So I think this week's going to be the last week of lectures, and then we'll transition to labs. We can talk about the details of that. Any logistical things I want to cover? So I have everyone turned in their lab 2 reports. So we're working through those, and we'll attempt to get those back to you by sometime around the beginning of next week. I haven't read through them in enough detail at this point to give you any feedback on them at the moment. The only thing I will mention is it was cool the number of unusual flock configurations that people were able to get. This is actually when I was putting that lab together, I didn't realize that by changing the parameters, you could get them to form like crystalline looking structures and get them to form weird sort of semi-rigid patterns. So that was cool to see. And the pictures of them, the flocks in those configurations in your reports are pretty cool. So that was a cool surprise, I guess I will say, about that lab. My plan for today is, at this point in the semester, we've gone through a fair number of the hardware peripherals that are available on the PIC, but not all of them. So what I'd like to do today is walk through a few of the ones that we haven't used in labs at this point, and that we won't end up using in labs this semester, mostly so that you're aware that they are there, and so that you are approximately aware of what they do and a little bit of how to use them, so that if any of these things are useful for your final projects, you know that they exist and that you can go use them. So there's just a handful that I want to go through, and then with any remaining time, we'll do what we've been doing, which is what tends to happen at the end of lectures at this time in the semester, which is talk about final project ideas. So, are there any questions from anyone right now? Logistical or otherwise? Questions about Lab 3 or Lab 4 or final projects or anything?
I have a quick Lab 4 question.
Okay.
I was reading through the timer documentation, and there's 3 different modes for the timers, and my impression is that you can chain 2 16-bit timers together in any of those 3 modes, but I might be wrong. Which mode are we supposed to be using?
Which mode are you supposed to be using? So I have to remind myself what the available modes are. Do you remember offhand what the modes are?
No, but I have it written down.
Okay.
There's synchronous clock, something I can't read, synchronous external clock counter, and gated timer modes.
So the gated clock time mode is meant for measuring intervals of time. So you can gate the clock from a external pin. Synchronous means that it's locked to the system clock. And asynchronous mode is you put on some random oscillator on a certain pin, and that then drives the timer at that frequency.
So
Everything we're going to be doing in this course is in synchronous mode.
Okay. Thank you.
And the timer, you are constrained to in which, maybe you're already aware of this, but I'll just clarify. You're constrained a bit in which timers you can chain to other timers. So timers 2 and 3 can get chained together, and I think timers 4 and 5 can get chained together. But you can't chain arbitrary pairs of timers.
Yeah.
So for this project, if you were to take that approach, since timer 1, really either of those 2 options works for you, because the only one that isn't available for you to use is timer 1, which is being used by the threader.
Okay. Thank you.
Any other questions for anyone? Okay. I still don't have your googly eyes on the robots, but that's going to happen this week. So keep an eye out for that. If any other questions occur to anyone, just interrupt me, but I'll get started on some of this stuff for today. So I'll start by just reminding you of this picture that we spent some time looking at in the first couple lectures of this class, which attempts to capture all the hardware peripherals that are available for you to use here, and then illustrate that we configure and control those hardware peripherals with plib, and then organize our software using proto-threads, and suggest some places to go look to read about each of these things in a bit more detail. So I'm bringing this back up just because we're sort of reaching the end of the lecture part of this course. So I want to highlight the things that we have talked about and point out the things that we haven't talked about yet in this class, but that are still here for you to use in your final projects if you so desire. So at this point, we've used and discussed the SPI channel. We've used and discussed the UART channel and the I/O ports. We've discussed but haven't used the I2C channel. I'll talk a little bit about this real-time clocking calendar today. I'm going to talk about this charge time measurement unit today. We've, of course, used the ADC quite a bit. I'll talk about the internal comparator some more, and the associated comparator reference voltage. I will mention the Watchdog timer. We've talked about DMA. We've talked about timers. I can talk a little bit about the non-volatile memory. And we've, of course, talked about interrupt functions. And I can mention a few of these other things as well. But I'm just reminding you basically of this list of peripherals and encouraging you to go double check this list to see if there's anything here that perhaps we haven't used in a lab that might be of relevance for you in a final project. So I'll start by just reminding you of, these are the slides from lecture 2, I think. So this is stuff that you've seen before, but it's been a long time. So let me just remind you of a few of these things. Let me remind you of the input capture module, which is available for you to use. What this input capture module is essentially a register with some event as the capture trigger and an input which is a timer. So the value contained within this register is some timer value that's changing, clicking. And then in association with some event, could be the rising edge on some external pin, could be some internal signal. The value of the timer gets stored in the register, it gets captured, and then you can go read the value of that register to get a very precise measurement of timing associated with some event. So if you were trying to measure very precisely the amount of time from some starting event to some ending event, you could zero this timer and trigger that perhaps it's the charging of a capacitor, right? So you could zero a timer and start charging a capacitor simultaneously. And when that capacitor reaches some threshold voltage, you would capture that time in an input capture module and then convert timer cycles to capacitance. This is an example of how this sort of thing might be used. But it's a hardware peripheral that's used for very precise timing. And I'll show you some example code of this in just a second. I'll just show you basically where the example code for this exists. So in the event that it's useful for you, you can go find it. But this input capture module it's often useful in collaboration with another hardware peripheral. And the example that I used in lecture 2 was to tie this thing to the internal comparator unit. This internal comparator unit is, you all remember comparators from some sort of a circuits class, but it's a very simple op-amp circuit where you can tie the internal positive and negative inputs to this op-amp to an external signal if you want. So you can map that to an I/O port and plug in to the positive or negative inputs to this op-amp. Or you can tie each of these to some sort of an internal signal, either ground or a reference voltage. And the notion here is that if we tie the negative input to this comparator to some configurable internal reference voltage, then when the input to the positive input of this op-amp goes higher than this reference voltage, the output will snap high. When it goes below this reference voltage, the output will snap low. So we can use this sort of circuit as a triggering mechanism. And you've all likely done this in one class or another. But there's a handful of these comparators that are internal to the PIC32, and you can map each of these inputs to external or internal signals, and then you can map this output either to an I/O pin, or you can use that internal signal name to map to some other piece of internal hardware. So how might you chain these two pieces of hardware? Well, an example might be, suppose that you wanted to measure capacitance. And as I think I mentioned in lecture 2, in previous semesters, this has been lab 1 for this class. It didn't make a ton of sense to make this lab 1 for the class this semester just because, well, we can't really plug things into breadboards and such, so it's not super well suited for remote learning. But in any case, you might consider chaining these two hardware peripherals in the following configuration to do something like measure capacitance, where the idea would be you have some capacitor here that you want to measure the capacitance of. You've hooked up an RC circuit here, and at the same time, you would discharge this capacitor, and then at the same time, you would start charging this capacitor and zero this timer, which is feeding the input capture unit. So this capacitor would start charging up, start charging up, start charging up. You will have mapped the positive input to this comparator to an external I/O pin, and you're comparing this positive input to an internal reference voltage, which you've configured. The notion here is that when the voltage on the capacitor exceeds this reference voltage, the output here will snap high, which means so the output here is mapped out of an I/O port into a separate I/O port and into the input capture module. This is the trigger. So when this output snaps high, the input capture module will grab the timer value at that time so that you can get cycle level precision of the amount of time that it took for this capacitor to charge in timer units, which you can then convert to seconds or milliseconds, and then you can convert that to capacitance. Makes sense why this is useful. So this is allowing for you to do timing, and it is eliminating the overhead associated with doing things like getting into an interrupt service routine or getting out of an interrupt service routine. This input capture module captures the time, and it can be configured to throw an interrupt flag to say, hey, I've got a sample ready for you to read. And then in an interrupt service routine, you would go get the value out of this register. But the value of this register is stored and static as soon as this triggering event occurs. Are there questions about this?
If the ratio of accuracies is really quite high, the comparator the input capture will give you a time estimate good to 40 nanoseconds, 25 nanoseconds. And about the best you can do with an interrupt service routine is probably 20 times worse.
So let me just show you if either of those two hardware peripherals seem useful for your particular final project idea. Let me just show you where to go find some more resources on them. On the time web page, you can see that this web page describes timers, input capture, output compare. It's useful for lab 4. Oscillators and the real-time clocking calendar. On here, if we scroll down, there's some information about timers, information about the real-time clocking calendar, and then information about these input capture units. And there is an example here, a simple example that shows how to set these things up and how to use them. And I'll just point out a couple of things about this example. First thing I'll point out is that the input capture units are configured down here in main, and the configurations there aren't tremendously many configurations. They're, as compared to some of the other hardware peripherals, they're quite simple to set up. And then the other thing that I will just point out, I just mentioned this, but I'll show it to you in code, is the way that this is used is you can see we configure, where am I looking here? We configure the input, where am I looking? We configure the input capture module here, and then we set up the interrupt associated with that input capture module so that when there is something to be read, an interrupt is thrown, and we have an ISR written associated with that flag, input capture 1 vector. And then within this ISR, we store the value in that register in some variable, which we can then do math on to convert to whatever units are most appropriate to us. But I'm just pointing out that we are reading the value of this register in interrupt service routine, but the value is stored in that register before we get into that interrupt service routine. Okay. And if this loads, I will just point out that there's the section on the input capture modules can also, the section of the hardware manual on input capture modules can also be found on this page. And it's sort of useful to look, as we have with many of these other hardware peripherals, it's sort of useful to look at the control registers. So if you care to, you can find the control registers here. And of particular interest, perhaps, are the library of modes in which you can open these input capture modules. You can open them in simple event capture mode. What you're configuring here essentially is, do you want for this thing to capture every time some triggering event occurs, or do you want for it to capture only once after the first triggering event occurs? And do you want for the triggering event to be some rising edge, some falling edge, or both? So a lot of the same configurations that you might imagine for something like an oscilloscope, but those are the configurations that you're setting up with this mode selection bit. So depending on your application, you should pay attention to the various options that you have when setting up this particular peripheral, and set it up in whatever way makes most sense for you, if you're going to be using this. Okay. Questions about this? Is it clear what this is for? The sorts of things it might be useful for? Okay. The other peripheral that I'll mention, and this is the one that I just mentioned, is often useful or can be useful in collaboration with that input capture module, is the comparator. And I can show you that if you want more information on the comparators, there's a comparator webpage, which links to the other sort of the official documentation for the comparator as well. And I will just point out that if we look at the block diagram here for these internal comparator modules, this is showing you what I just recently suggested, which is you can tie each of these inputs to some sort of you can map the C1 in comparator 1 positive input to an external I/O pin. These are mappable through peripheral pin select. Or alternatively, you could tie the positive input to the reference voltage. And the negative inputs as well, you can map to I/O pins if you so desire, or you can map that to some sort of internal reference voltage. And then the output here is called C1 out in this case, C2 out for the other comparator. And that too, through peripheral pin select, you can map to an I/O port if you want, or you can keep that as an internal signal and manipulate it internally. Okay. Questions about this stuff? Okay. Now I mentioned the capacitor example specifically because the next peripheral that I want to show you is one that makes doing things like measuring capacitance of a capacitor quite simple, actually. And it's kind of as far as I can tell, it's kind of a unique hardware peripheral as far as other microcontrollers go, but I could be wrong about that. And that's this charge time measurement unit, which is essentially the charge time measurement unit is a configurable constant current source within the PIC32, where you as the user can select the amount, you can select from a few different options of the amount of current that you would like to be supplied to some test article. And what's interesting about this is it is hooked up, it is attached to the analog to digital converter, and it's also attached to comparators. So you can do things like supply constant current to some test article and then measure the voltage across that test article using one of the ADCs. And the usefulness of something like that is some of the applications are probably kind of obvious to folks. So for example, this makes something like a resistance ohmmeter quite simple to build, right? You have some resistor, you set it up and use the CTMU to supply a constant current to it. You measure the voltage across that resistor by means of the ADC, which is hooked up directly to the charge time measurement unit. And you know I, you know V, and you can solve for R. So it makes things like measuring resistance quite easy. It also makes things like measuring capacitance quite simple, because you'll remember that the equation for the current across a capacitor is the current I equals the capacitance C times dV dt, right? So if you hold I constant, then you know I. If you supply currents for a certain amount of time, you know T, you know dt. You can measure the voltage with an analog to digital converter, so you know V, and you can solve for C. Right? So it provides a very simple mechanism for measuring absolute capacitance, and it also provides a mechanism for measuring changes in capacitance. So you can supply a certain amount of current for a specific amount of time to some capacitive test article and be sampling the voltage after that amount of time. And when the capacitance changes, the voltage that is achieved after a certain amount of time supplying constant current is going to be different. Do people know the sort of so what sort of application is a change in capacitance useful for? Where you don't necessarily care about absolute capacitance, but you care about the capacitance changing. Guesses?
You use them every day, all day.
This makes a wonderful touch sensor. A wonderful touch sensor. Your body has a certain amount of capacitance. I think it's tens of picofarads or so. So if you have some capacitive test article and then you touch, maybe you're measuring the capacitance across some pad on a PCB, right? And you touch it, your body is acting as a capacitor that's in parallel to the capacitance that was already there. A capacitor, your body is something like tens of picofarads, I believe. So with this charge time measurement unit, you will be able to detect a measurable difference in the voltage that was achieved through that capacitive test article in the amount of time that you supplied constant current. And you can register that change of voltage as a touch event. Or even as a proximity event. As your hand gets close to stuff, the capacitance of things can change. So it's difficult this semester, of course, but if you wanted to, in your own apartment, build some sort of a device that took action when you waved your hand near it, you could use a hardware peripheral like this, or you could build something like this, to measure changes in capacitance as you wave your hand over something, and take some action accordingly. And there are some devices that do this. Has anyone ever heard of, what's the name of that, Bruce, you might have to help me out, that instrument, the capacitive instrument, theremin, is that it?
Yeah.
Theremin, yeah.
Okay. If folks haven't seen, if you go on YouTube and Google theremin song, something like this, and watch people play these instruments, it is a musical instrument based on the idea that as you move your hand closer to this test article, which serves the role of the instrument, you're changing the capacitance, and the output tone changes in accordance with the capacitance so that you can sort of wave your hands around this thing and create songs. Apparently very difficult to learn, but pretty cool. Very sort of a deeply physics and electrical engineering-y kind of instrument.
there's one other thing you can do with this, which is sort of less obvious, and that is that if you just hook a capacitor up to the constant current source, and then use one of these external edge trigger pins that are on the left side of the diagram, you can turn on and off the current source very quickly. And so you can measure extraordinarily short times by measuring the voltage that appears because you're charging a capacitance with a constant current. So you get a voltage which is linear with time, which suggests distance measurements. I believe you can get down to a nanosecond with this, which is 1 light foot.
Has anyone ever attempted that in this class?
No, but it would be interesting to see.
Okay.
A fairly low precision LiDAR.
Okay. I will just point out that on this webpage too, the hardware manual section for this device is linked up, containing some of the same block diagrams, the ordinary control bits that you can look at, and one of the big applications that they expect people to use this for is doing things like measuring capacitance and relative capacitance. So there's a whole section here on that, which you can read about if you so desire. And they suggest a sequence to execute in order to use this to do something like measure capacitance. So it's quite well documented, and if it seems useful to you, this is where the documentation lives. The other interesting document that I'll point you to is they prepared this "What can you do with the CTMU?" which suggests a whole bunch of various applications for how to use this device to do various things. So the big one, the first one is capacitive touch sense control, which we already sort of discussed. They talk about using it to sample a microphone as a proximity sensor, a stud finder, liquid level sensing, all sorts of things that get sort of increasingly interesting. Many of them sort of fundamentally associated with measuring something like capacitance, but not all of them. Some of them are a little more exotic. Humidity sensing, which uses changes in, it associates changes in relative capacitance with the humidity in the air, which is kind of interesting. And these get sort of increasingly interesting and exotic, all the way down to, one potential application being solving world hunger. Mass deploy inexpensive temperature and humidity sensors, blah, blah, blah. And then I like it when there's little pieces of humor left in these documents, but they say another application is to create world peace with this device, but that's left as an exercise to the reader. In any case, it's a very well documented peripheral. It's kind of a unique peripheral, and it's interesting to think about clever ways to use it. And there's lots of documentation on it and lots of suggestions. So if you think this would be useful for something that you would like to do, consider using it. Of course, you're a little constrained because your ability to hardware prototype is limited this semester. So that's going to limit to some extent the usability of stuff like this. But it may still be useful for some folks. So I just want to make it clear that this is here. Okay. Questions about this? Constant current source hooked up with an ADC internal comparator. What could you do with that? Okay. I will mention too, going back to the time page. By the way, just a reminder that all of these links are here. Talked with some groups that perhaps folks are forgetting that all these links are here. There's a huge amount of documentation down here for you to go explore. some interesting reading here. Well, it's fun to go explore the links on these pages. Not all of these are directly related to this class. Down here, there's a bunch of links on the computer history, which are really interesting. Some very interesting reading about plagiarism events in this course. Not events where 4760 students committed plagiarism, but events where researchers elsewhere plagiarized 4760 students. And this is all Bruce's documentation, but it's phenomenally interesting reading to learn about the mechanisms by which that sort of thing is corrected. Anyway, if you want to go read about that, you should go check it out. But I will point you to time here. And I want to talk a little bit about this real-time clock. Probably you're not going to be able to use the real-time clock this semester because it requires an external oscillator, which is not hooked up. But I'm pointing this out because if you want to go do projects with the PIC32 after this class, good to know that this exists. But what this does is allows for you to build things like alarm clocks and such. It keeps track of time in hours, minutes, and seconds for up to, I believe, like 100 years or so. And it allows for you to set alarms. So you could build a project where the user is able to say, fire an alarm, at this specific time, 8 a.m. on Thursday morning. And you'd be able to do that with something like a real-time clock. Anything you want to say about the real-time clock stuff? There have been a couple projects that have used this, I've noticed on the course website. One person built a model of a digital clock that appears on a wall in New York City, I believe.
The oddest thing about the real-time clock is that the registers all read back in binary coded decimal, not in binary. They're in BCD. So you have to watch that when you read it. But you can expect with a $1 oscillator, you can expect accuracy down to about 10 parts per million in time, which corresponds to there's pi times 10 to the 7th seconds in a year. So that's call it 30 seconds a year accuracy. And also, if you're ever going to actually do this, don't use a 32768 crystal. Spend the extra 30 cents and buy the encapsulated oscillator. It's so much easier.
And then the other thing on the timer page that I will just point out is, because maybe this is useful for you, perhaps, there is a Watchdog timer. The Watchdog timer, many of you are likely aware of what these things are for, but essentially this is a timer that will count to a certain threshold, and if the timer overflows, reaches the threshold to which it's configured, it will cause a system reset of the CPU. So the idea is that in your main program, as the program is running, you would be clearing this Watchdog timer to prevent a reset. But if your program were to hang, there was some problem that caused something to hang, this Watchdog timer is a mechanism by which you could do a reset to try to get the system back online automatically. Okay. Your projects should not require a Watchdog timer. At least I don't think. Maybe, well, it's difficult for me to even come up with an application in this class where that would be really required. But this is nice for something, if you're deploying some device in a field somewhere and you want for it to be persistently operating for a very long amount of time, a time that is so long that it's difficult to test reliability over that amount of time. then something like a Watchdog timer is nice, because if some obscure event causes a corner case problem that only occurs maybe once every 2 months or something, well, then there's a mechanism in place to just get the system back online, right? If this is in some hard to reach physical location that you can't go monitor it, a capability like this is nice.
But you're quite right. Your code should never depend upon the Watchdog timer. It is really a last resort recovery from, say, a cosmic ray strike or being dropped off a building or something like that.
By the way, this is totally an aside, but that cosmic ray strike kind of event is, and a problem with the Watchdog timer, is exactly the event that killed one of the satellites that my PhD group launched. It was a CubeSat with avionics in it based on microcontrollers and such, and there was a Watchdog timer in there. And it was deployed from the space station. When you deploy things from the space station, you are not allowed to do anything for most spacecraft, it's 30 minutes, because they're worried about things. They don't want you twisting around. They don't want you doing anything. You're just supposed to be a rock. Not even really do radio transmissions for 30 minutes. We were deploying a bunch of those little chipsats, so they wanted us to wait even longer. I say us, it was actually the grad student before me. So there was a timer in there counting down until deployment would occur. And what happened was, it was like 3 days that the satellite was supposed to wait and then deploy. A cosmic ray hit somewhere just in the wrong place, which caused a system reset, which caused that counting down timer to also reset, which means it was going to wait 3 more days from when it was originally supposed to wait. And by that time, the whole satellite had burned up in the atmosphere. So it just one of those obscure events, but something to think about. Okay. What I want to talk about a little bit with just the remaining time is many of you have likely done this already, but all of the final projects from previous semesters, the documentation for them is listed here. And you can click through these things and see what previous folks have done. For example, this is the project from your TA, Megan. And you will be asked to do something similar, which is essentially create a website which documents the project that you've created. And what I want to point out is that there are some down here which are not made public. And I want to just spend a few moments talking about why might you make a project public? Why might you make a project non-public? And I briefly mentioned this at the end of a lecture, maybe last week, but I'll just mention it again. If you create something that you think you would like to patent, if you publish your work like this on the course website, that counts as an IP disclosure. I'm not an IP expert. It's more complicated than you realize, this whole IP world. So I'm not an expert, but what I can tell you is when you do an IP disclosure, you are starting a clock that is counting down from 1 year. So you have 1 year to file for, I forget exactly what you file for. It's a provisional, perhaps. To take some action, you have 1 year in order to secure that patent. If you make this thing public. If you don't make this thing public, then it doesn't count as an IP disclosure and you have more time.
Also, there's the added wrinkle that the 1 year countdown only applies in the US. In the rest of the world, as soon as you pull the trigger and put that on the web, you can no longer patent it. So if you think there's a patent opportunity, think carefully about putting it on the web. Part of the write-up is you have to claim whether you want it on the page or not.
But it is, if your project is one that doesn't necessarily lend itself to patenting, it is quite nice. We appreciate when you make your project public for a lot of reasons, but one of them being, US students now, it's useful to go back through previous students' project and learn what was done and generate ideas and that sort of thing. And they're cool, we like to make them public. So
it's great documentation for the course, but it is also useful for you because let's say 3 years from now, you ask for a recommendation from Hunter. It's a lot easier to remember you and your project if we have it linked up. And you may find that it's useful to put on a resume or to use in a job interview to be able to point to, say, a video of what you've done, because as we all know, video sells.
So as you're working on your final projects, I would ask that you also treat this as, the sun's coming out, sorry. I would also treat this as an exercise in documentation. Try to really document this project in a way that is, that years from now you can go back and look at your documentation and it's still useful. The longer I've been doing this stuff, the more deeply obsessed with documentation I've become. It's really, really important. It allows a project, as soon as you have finished a project, there's a huge amount of value in it for you because you've just learned about a bunch of stuff, right? So it's extremely valuable. If you don't document it, the value associated with that project drops really quickly. And a year after you've completed a project that you don't document, there's not that much value left often. A lot of the stuff that you will have learned may have atrophied. So documentation is a really good way to allow for a project to retain its value for indefinite periods of time. In a bunch of ways, right? In a bunch of ways. So take the documentation aspect of the final project extremely seriously. Any questions about this? Okay.
Strongly recommended that you read the write-up requirements, which are in the lab write-up, because there's lots and lots of detail about what you have to do.
Okay. Ooh, blinded. Stop sharing. Okay. So we have, 5 minutes remaining. So can we hear some other, so I've heard final project ideas from Alex and from Parth and a little bit from Kat. Does anyone else have anything specific or even quite general that they're thinking about? Okay, start thinking about it. And we can kick around ideas in the lab too. Is there anyone that is leaning in a sound synthesis direction?
We were thinking of doing some random sound generation. There was a project, I think this was a 5760 project where they used a Conway's Game of Life on the display, and then a single line would go through the whole screen, and whenever it would hit a pixel, it would generate a beep or like a certain kind of sound. So depending on the visuals on the screen, you would get different kinds of sounds. We're trying to do something similar, except we want it to be coherent, like have some kind of rhythm or beat, so that it does sound nice, and hopefully surprises us and like makes new sounds. There was this one we found which had a Markov chain thing to it, that you gave it some inputs, but then it predicted new sounds and it predicted new sequences for you. So we were looking into that.
That project worked remarkably well. Where the Markov process was trained by using a fairly long MIDI file, which in which there's no documentation, And the music it produced had a vague similarity to the input music because it was statistically similar.
Mm-hmm.
The other, this is a little bit different than what you just suggested, but it reminded me of this. Maybe it's of use to other people. Bruce and I had an MEng project proposal that ended up not getting selected by anyone this semester, but the observation is that your ears are, in many cases, just as good, and in some cases better at pattern recognition than your eyes. So if you have some process taking place and you can associate that process with audio so that you can listen to it as opposed to watch it, it can be the case that your ear picks up patterns that your eyes may have missed. So the specific application that we proposed for this was, what if you built so you're all familiar with like the Lorenz attractor, it's the strange attractor, the pretty butterfly chaotic system. What if you associated positions in 3D space with sounds of one variety or another? Maybe X position is one frequency, Y position is another frequency, or Z position is something else, or some mapping of position to sound so that you could listen to the oscillator instead of watch the oscillator. Could your ear classify that as chaotic? Does chaos sound like something? Maybe Bruce has some clarification of that, but I think it's a cool idea.
So we were sort of just scratching our heads and bouncing this around. So the part of the problem is to come up with a mapping that makes sense. And I don't know what that would be, but you certainly have lots of degrees of freedom you can manipulate with sound. Yes, our ears are really good at sequences of a certain periodicity. We're not very good at sequencing above about 5 hertz or so, or lower than maybe a millihertz. But in that region, you can detect a lot of patterns with your ears you can't detect with your eyes.
By the way, for the sort of mathematically geeky among you, this observation is exploited in, I don't know if anyone has explored the online encyclopedia of integer sequences, but for people that like integer sequences, it's just this repository of folks that have come up with all sorts of just arbitrary rules for generating sequences of numbers. And on that repository, they provide you with a graph of the sequence so that you can see visually how it evolves. And they also, for many of these sequences, associate the sequence with music so that you can listen to the sequence. And this is because your ears are good at picking up patterns and your eyes are also good at picking up patterns, but sometimes your ears are better. So you can go listen to sequences in addition to watching them. And if you want to go listen to a sequence, what's the name of the one? I don't remember the name of it, but if you Google number file integer sequence spooky, there's one that generates a sequence that sounds remarkably like a suspenseful scene in a horror movie. It's really cool. So they're fun things to play with, but it's, like I said, it's based on the observation that your ears are just as good and sometimes better at pattern recognition as your eyes. You're muted, Bruce.
Sorry. The slightly spooky Rockamon sequence.
That's it. That's it.
The chaos game. Oh man, I gotta go here. I haven't.
Okay. Well, so we're out of time. If anyone has any questions, I can stick around for a little bit. But otherwise, I will see you folks on Wednesday. Wednesday might be the last time we get together before transitioning to labs, either Wednesday or Friday, but I'll decide this week.
This would be a great week to be prepared, for students to be prepared to talk about final projects in lab.
We'll ask you about them.